Namaskar. A very good afternoon to you all. I welcome you all to the session on electromagnetic spectrum. To deliver this session, we have with us a very distinguished speaker today, Dr. Somak Rai Chaudhary, who is the Vice Chancellor of Ashoka University. He has undergraduate degrees from Presidency College, University of Calcutta, and University of Oxford. After his PhD from the University of Cambridge, he worked at Harvard Smithsonian Center for Astrophysics, where he was also the part of the team that has built the famous X-ray observatory for NASA. After teaching for over a decade at the University of Birmingham, UK, he returned to India as Dean of Sciences at Presidency University, Kolkata, and went on to become the director of IUCA, Pune. Dr. Roy Chaudhary is a fellow of the National Academy of Sciences. His research involves a wide range of topics in cosmology and astrophysics from the ground and from the space. Sir, I formally welcome you to this session. And the audience has been briefed about space environment and orbital mechanics in the previous sessions. Sir, over to you from IIRS.
Thank you very much, and thanks very much for giving me this opportunity to address so many students. The ISRO Start program is always a fantastic program for beginning physics students to understand astronomy from space, from various things that we do. And I want to begin today, and I'll come back later on at a later lecture on much more detailed activities. But I want to people to understand why we do astronomy from space and what information space astronomy can give us. For doing that, we have to study everything about the electromagnetic spectrum. You see a very colorful picture on the screen now, and this is actually a composite made from observations of the sun at different wavelengths, different parts of the electromagnetic spectrum. And you can see how different the sun looks at different parts of the electromagnetic spectrum. In some places, it doesn't have any feature at all, but in other wavelengths, it has a lot of features. Even within the ultraviolet part of the spectrum, these are pictures taken by ISRO's own Aditya L1, the SUIT instrument, which was built at IUCA when I was the director of IUCA and was very involved in building this instrument. You can see that even within the ultraviolet range, the sun has so many different ways of expressing itself. And that tells us how the electromagnetic spectrum plays an important role in astronomy. What is the electromagnetic spectrum? You know that electromagnetic waves are waves that waves are things that transport energy from one part of the universe to another. And the way we receive energy of any form from other parts of the universe is mostly, till now, has been almost exclusively through electromagnetic waves, which are generated by electromagnetic disturbances in celestial objects, and that generates different kinds of waves. Very recently, we have also started detecting gravitational waves, which are a different way of transporting energy from one part of the universe to another. And I'll speak a little bit about that, not in today's lecture, but later on in another lecture. But if you look at the electromagnetic waves, you will see that the kind of waves that we are familiar with, which are optical, which our eyes are sensitive to, is only a very small part, which I call visible light here in the middle of this diagram. It shows that there is a whole continuum of different kinds of electromagnetic waves. You can have, and it's characterized by its wavelength and frequency. You can have short wavelength, long, high frequency waves such as X-rays and gamma rays, ultraviolet, on one side of the visible light, and the other side you have low energy waves such as infrared, microwaves, radio waves, which have longer wavelengths. And you can see that in different parts of the electromagnetic spectrum, seeing is very different because things look very different in different parts. You can see that, for example, when a black bag, plastic bag, in normal light is opaque, but it can become transparent when seen in the infrared. Butterflies look very different in the infrared, or our own body. There are parts of the body that actually glow in the infrared, and but we of course don't glow in the dark in optical light. So things appear very different, and throughout this talk you will see how we get information about celestial objects at different parts of the spectrum, and thus understand more about what they are. You can see how the sun I showed you before, a composite of this, looks very different in the visual, which is the visible light. You see sunspots, but not much at all. But once you go into the UV and X-ray, these are all taken at the same time of the sun, and you can see small spots are actually large magnetic storms, and they show up in the X-ray and the UV, but of course in the visual you don't see them. Similarly, galaxies look very different in different parts of the spectrum. In the X-rays, you don't see the features that you see in the ultraviolet and visual, and these are the spiral arms and the star-forming regions and things like that. So what are these electromagnetic waves? How do we characterize them? We characterize them, as I said, through I'm assuming that they are a kind of wave, and from Maxwell's equations, you get the mathematical form, as you know, of electromagnetic waves. And it shows us that this energy that propagates through the universe and comes to us from these celestial objects, the sun or the stars or the galaxies, they would reach us, and they move through the universe in the form of waves, which has a wavelength. And this illustrates what a wavelength is. And the higher the wavelength, the lower the frequency, because the frequency and wavelength are connected through this equation, c being the speed of light. It is the product of the wavelength and the frequency. And so the higher the frequency, the lower the wavelength. And only one small fraction of the entire spectrum of electromagnetism or electromagnetic waves are apparent to our eyes. You need instruments to see the other parts of the electromagnetic spectrum. And you can calculate one from the other. For example, if you have just from that formula, so if you, for example, have a light that you see from a laser pointer that has a wavelength of 663 nanometers, you can use this simple formula to transform that into a frequency that will come up to be about 10 to the 14 hertz. And so you can see that as the wavelength decreases, that frequency will increase. And you probably know that through quantum physics, the energy of a photon is proportional to the frequency, E equals h nu, and so the energy of the photon would also be higher if the frequency is higher and the wavelength is lower. So this is, again, something that's taught in all physics classes. Black body spectrum. A star is a black body, and so when the star has a certain temperature, it shows up in a whole spectrum spread over this electromagnetic the wavelengths that I talked about. Our sun, for example, has a surface temperature of 6,000 degrees Kelvin. You can see in the middle the spectrum here, and that is why it peaks at about a wavelength of about 500 nanometers, 5,000 angstroms. If the star is hotter, say 12,000 degrees or 20,000 degrees, as newborn stars are, the peak will appear in much, much shorter than the limit of our eye, and it will be mostly emitting in the ultraviolet. 250 nanometers is in the ultraviolet. Our eye sees about 400 to 800 nanometers. And if it is a much cooler star, like 3000 Kelvin, it will emit its peak in the near infrared, which is again beyond our visual limit. So the stars that we see in the sky with our naked eye are very much like the sun. We can't see predominantly the light that comes from much hotter stars or much cooler stars. And this also is covered quite a lot in undergraduate programs in astronomy, the fact that the total amount in physics, total amount of light that comes from a black body is proportional to the T to the power 4. So the hotter the star is, the brighter it is. So this lays the basic fundamental principles of what we are going to talk about in terms of electromagnetic waves. It will show you that in different parts of the spectrum, we will be able to see different physical processes, which will give us different parts of the aspects of the celestial objects that we see. Astronomers have a disadvantage that they cannot go and actually touch or observe the objects that we see. Somebody who's studying a mouse or a fly in a lab can actually touch them, but we can't. And so we are totally connected to the Earth, and we cannot travel to the star or the galaxy that we are studying. And so the only thing that we get is electromagnetic radiation from these objects, and we have to infer what we are studying from the electromagnetic radiation. So I put this slide in to remind you that we are now looking at a whole range of wavelengths, going from radio waves, which is of many meters to millions of meters, to all the way to gamma rays, where the wavelength would be of 10 to the power minus 14 meters or 10 to the minus 12 meters. So we have a range of 15 to 20 orders of magnitude of electromagnetic radiation that we can currently now observe. Why is this important? This is important because the atmosphere of the Earth actually lets in only a small fraction of all the electromagnetic waves that come from outside the atmosphere. And this, as you can see, our eyes see optical light around 400 to 800 nanometers, just short of 1 micron. And that is where the atmosphere is also transparent. And so we can see the stars. If our eyes were sensitive only to ultraviolet, we would not have seen the stars. And there is a window also in the radio region, which lets in the microwaves and radio from distant objects. Elsewhere in the electromagnetic spectrum, if I have to observe anything in the ultraviolet, in the near infrared, far infrared, or X-rays, gamma rays, we have to go to space. And this is why we are having this whole course on astronomy from space, because astronomy became and astrophysics became a very, very mature subject only when we could go to space and observe everything in all these different parts of the electromagnetic spectrum. And that only happened in the last 50 years. And that is why before that, we did not know a lot about the mysteries of the universe. This is why also astrophysics from space is very, very important. So you can see in the different parts of the spectrum, we have, gamma ray, X-ray, we see very different things. And particularly because of that black body spectrum I showed you, if you look at just the thermal nature of objects, you can see that in the gamma rays, you see gas that's moving at relativistic speeds and also thus has temperatures that are more than 1 billion degrees hot. You can also have X-rays coming from hot gas that's 10 million degrees or 1 million degrees hot. Ultraviolet will be seen from hot stars that are new stars, newborn stars, which are maybe 10,000 degrees to 20,000, 30,000 degrees hot. Optical stars our optical light comes from cool stars like our sun, which is a few thousand degrees hot. Then the infrared will come from in between the stars, the cool gas and the dust that there is in the galaxy. And that emits things in that range of 10 to 100K, that kind of temperatures. Our bodies are also that kind of temperature. And we emit infrared, near infrared, for example. And then millimeter waves would be, for example, the cosmic microwave background, the Big Bang afterglow, and things like that. And so I will cover we have very little time today. I will cover a few of these wavelength regimes to show the different things that we can see. And now from space, in the regions of the electromagnetic spectrum, we can observe objects which we wouldn't have seen from the Earth in most cases. Of course, infrared astronomy began from Earth because in this range of 700 nanometers to maybe about a micron or so, we can observe the sky. The atmosphere actually lets in. This is the transmission of the atmosphere. In this range, you can see 1 micron to 5 microns, and you can see there are certain parts where the transmission can happen. Light can come through, and but then and that this is because the waves of this wavelength are absorbed by water mostly, and other molecules in the atmosphere, carbon monoxide and various other things that have their rotational and the bands of energy in this region. So you can, if you go far above the highest clouds in really the highest mountains in the world, you can actually observe near infrared very nicely. We can do that from Ladakh, our own telescope, Himalayan Chandra telescope. And you know that in the current budget, the Indian government has actually sanctioned to repair and enhance the Himalayan Chandra telescope, which is incidentally the highest telescope in the world. It is at a height of more than 5,000 meters above sea level. And there the budget has also made a provision for a large, about 10-meter optical telescope to be set up in Ladakh. But there are other telescopes like the ones in Hawaii, which are also at this height that you can observe. So you have the Keck and the VLT that I've written here are high telescopes that can observe near infrared. However, if you want to observe in the full range of near infrared and go up to far infrared, then you have to go to space. And the best example of that is, of course, now the James Webb Space Telescope. That has been up there for about 3 years now. That has been launched by NASA, ESA, and the Canadian Space Agency put together. And it is a telescope which has a mirror that is cooled to very near absolute zero. It's actually minus 220, minus 230 degrees Celsius. And so that the mirror itself does not emit the radiation that it is trying to observe. And then as you can see, there's a shield on one side. It is like an umbrella that shields the telescope from the sun, and so that the telescope can look away from the sun and with a cool mirror observe the universe. And it is doing amazing things that we could never do at these wavelengths, and these are wavelengths of a few microns. By looking at the distant universe, getting views that we could not get from the surface of the Earth. Here's a good example of what JWST has been doing. Here's a comparison between NASA's earlier near-infrared telescope called Spitzer, which was launched in the early 1990s. And you can see on the left-hand side is Spitzer's image of the same part of the sky, which includes a very famous dwarf galaxy called WLM. And on the right, you can see the James Webb Telescope's view of the same part of the sky. And you can see how different it is. You can see how a telescope in space that is really capable, a large telescope, and cooled so that the telescope itself doesn't have a high background, can open up the universe to us. You can see how detailed the galaxies are. And as you know from this telescope in the last 3 years, we found some of the farthest objects in the universe. Now, why are we finding the farthest objects in the universe with a near-infrared telescope in space? What we are observing is what we would have been optical light and ultraviolet light from the very bright stars. But when the galaxy that we are observing is at a very high distance, the highest distance from us, we call it a redshift, which means that as the universe is expanding, the very far away objects are moving away from us at very high speeds. In the universe, there's something called the Hubble law, which shows that the velocity of a galaxy that is moving away from us is proportional to its distance. So the further away something is, the faster its velocity away from us. And when it moves away from us, anything that moves away from us due to Doppler shift, their spectrum shifts towards the red. And the interesting thing is that the amount by which the wavelength shifts for a source that is moving away from us is proportional to 1 plus the redshift. So when, as James Webb has now discovered the farthest galaxy in the universe, and this is the one that we know, it's called MOM Z14. It is at a redshift of 14, and so its wavelengths that we see are actually what the wavelength that is there in the galaxy multiplied by 1 plus 14, and that is 15 times. So in this particular graph, you can see that what we are seeing is like the Lyman alpha hydrogen line, which actually is in the ultraviolet. It is about 200 nanometers, and it has been now shifted to 15 times its wavelength, and you're seeing it here at about 2 micrometers, right? And that is why we see with a near infrared telescope things that are very far away, because you can see the bright stars that are in the galaxy that would have been seen in the ultraviolet if we saw them nearby, but we are seeing them in the near infrared. And both the ultraviolet and the near infrared have to be seen from space. And this is why we need near infrared telescopes in space. Right now, India does not have a near infrared telescope. That is why I'm showing you uh, some measurements from NASA. But when I move to other parts of the spectrum, you will see that ISRO and India are doing very well in some other parts of the spectrum. Ultraviolet spectrum was the fact that ultraviolet is very important was first proposed by Meghnad Saha when he wrote the ionization equation and showed that most of the stars, the newborn stars, will actually be emitting in the ultraviolet. He actually even predicted that since ultraviolet radiation is stopped by the ozone layer, he knew this, and he predicted that we really need to send a telescope into space. And this is an excerpt from Harlow Shapley, a famous astronomer who wrote an obituary after Meghnad Saha died in 1955. He wrote that when Professor Saha came to visit Harvard, he was asking whether we could build a telescope that we can send above the stratosphere to observe the newborn stars that are now that can be observed only from above the ozone layer, which is 50 kilometers from the surface. It was Meghnad Saha's idea, which then transformed into the Hubble Space Telescope, which is, so you can call Meghnad Saha the kind of father of the idea that that gave rise to the Hubble Space Telescope. Martin Schwarzschild was the person who turned in that idea into reality. And in 1990, the Hubble Space Telescope was launched, was the first major ultraviolet telescope in space. And now, and so you can see how galaxies look very different in the ultraviolet. We now have our own ultraviolet telescope in space, and this is ISRO's AstroSat, which has on the same platform. It was launched in 2015. On the same platform, it has X-ray telescopes and ultraviolet telescopes, the EVIT, and has been doing amazing amount of work now observing, following Meghnad Saha's prediction, observing the ultraviolet universe in a wonderful way. And it is 650 kilometers above the Earth's surface, and it observes at the same time with 5 different telescopes, optical, ultraviolet to hard X-ray all together. And they all observe the same object at the same time. And 3 of the telescopes actually observe X-rays, which I'll talk about in a minute. And then one of them is the ultraviolet telescope. And it is now actually found lovely things again. These galaxies that are young galaxies that form stars in the ultraviolet, and these are in the nearby universe, not as far away as as I showed you in the near infrared, but the ultraviolet being actually redshifted into the optical or very near UV region, and it has found very spectacular galaxies in which can only be seen from space. This is the famous UV deep field from Kanak Saha and collaborators at IUCA, who's been now finding wonderful examples of ultraviolet observations. And you can again compare with NASA's Base Telescope, GALEX, which is on the right, and you can see the same part of the sky observed by AstroSat, UVIT, and GALEX, and you can see how much better AstroSat's telescope is. Now, I move on to X-rays, and X-rays are then more energetic than ultraviolet and shorter wavelengths. And these are X-rays that actually detect very hot plasmas. These are has to be about 10 to the power 6, 10 to the power 7 degrees Kelvin. What gets so hot? These are supernova remnants, for example, things that are stars that have exploded, or the gas that's inside the supernova around the pulsar, or it could be matter falling into deep gravitational wells in the centers of clusters of galaxies. You can see that there's a great picture of a cluster of galaxies on the left. It is the optical picture, and you can't even see, you can see there are lots of galaxies there, but you can't really see the gravitational potential well of dark matter around these galaxies. On the right, you can see the same cluster of galaxies, but in X-rays, and this is now ROSAT, an early X-ray telescope that the Germans launched, which is above the atmosphere, and you can see the hot intergalactic gas in between the galaxies. And you can see there are actually two clusters there, which you wouldn't be able to see on the left. Right now, you heard that I was involved in NASA's Chandra Observatory, which built X-ray mirrors and launched in 1999 a telescope where one can image X-rays, and you can actually image X-ray sources, which are X-ray binaries, which have black holes in them, or it can image clusters that have these very hot gas. And you can see in this mirror system, you have nested mirrors, because if you want to do X-ray imaging, you have to focus X-rays in grazing incidents, not normal incidents. And so these are very long mirrors, and you can nest those mirrors. Chandra has 4 mirrors nested with each other. The soft X-ray telescope at AstroSat, which I showed you, also has an X-ray telescope. This was launched in 2015, 1.5 decades after Chandra. And this is a picture of the AstroSat mirror, X-ray mirrors. These are gold-plated mirrors, and there are 40 mirrors in there, nested with each other. The Chandra one has 4. It's much bigger, much longer, but the SXT, the software X-ray telescope on AstroSat, also can observe the same things now, but at a smaller resolution. Here's an example of what you can do with the telescope. Here's an example of the Centaurus A galaxy, which is a nearby galaxy, an optical picture. But if you observe with the Chandra X-ray telescope, which is what I have observed quite a bit, with a very long exposure, you can see that in the X-rays, this looks like that. The same telescope where the optical light shows stars that are a few thousand degrees hot, but in the X-rays, you can see things that are 10 million degrees hot, 10 to the power 7 degrees hot. And you can see that the gas around the central black hole in the galaxy, you can see this is the optical picture, and this is the X-ray picture, is that hot, and it has emitted a jet. But there are all these small stars, which are X-ray binary stars, and many of them are black holes, and some are neutron stars, which are strong enough gravitationally that can emit X-rays. Okay. Can people hear me?
Sir, can you hear me?
Was I talking about this then, or was I? Do you know whether where
Yeah,
which slide where it was?
you were talking about X-ray observatory. Yes.
Yes. So I was talking about. Okay. Can I hope everybody else is there. I don't know what happened. I'm sorry. I dropped out of this, but I'm coming to the
It's
end of
okay,
my
sir.
talking now.
We're all there. Yes.
So I was talking about how in X-rays you see things that are a million degrees or 10 million degrees hot. Here we are when we look at a picture like this. These are normal stars, stars that we see with our eyes, and these are things that are many thousand degrees hot. But when we look at the X-ray view of the same galaxy on the same scale, we see things that are a million degrees hot. And what are things that get a million degrees hot or 10 million degrees hot? These are things, gas that falls into the surroundings of black holes or neutron stars. Can you hear me now?
Yes, sir.
way. Um, Let me just
Right.
quickly. So I will. If, are you going to look at the questions? If people have questions, I'll just wrap up in 2 or 3 slides.
Yeah, there are few questions from the students.
Yeah. So
So
let
I'll
me
be
just wrap
putting
up.
them to
Give
you.
me.
Yeah. Yeah.
Yeah. Give me. Just let me wrap up in a couple more slides. So I was going to
Sure,
say
sir.
that we have because we have to go to space to look at the sky. ISRO has a very extensive program of looking at different parts of the electromagnetic spectrum that cannot see celestial objects from the ground. One good example is Aditya L1, which now has been launched and has been studying the sky. I showed at the beginning of the talk some amazing pictures taken by Aditya L1. It has two instruments, one to look at the sun's surface and another the corona, and it sits about 1% away from the Earth, between the Earth and the Sun. Um, and this is a very, very exciting instrument. And I had the privilege of being at IUCA when we built the ultraviolet camera for it that produces these amazing pictures, a camera called Suit. And even the very first few images that came out from Suit were absolutely stunning in 2023. And I showed you at the beginning of the talk some of the new pictures from it. A very important X-ray satellite that was launched by ISRO is called ExpoSat. It looks at polarization in the X-rays from very high energy objects like AGN or, or binary stars, and this is a very unique instrument that was launched at the same time, around the same time as Aditya L1, built mostly at the Raman Institute in Bangalore. And for future missions, there are many very interesting things that are being considered by ISRO. ExoWorlds might look at the exoplanets, the atmospheres of exoplanets. CMB could be studied by CMB Bharat. Daksha is a fantastic program that follows up on gravitational wave detected sources, which I'm going to talk about in my next talk 2 weeks from now, and maybe we'll have a very important ultraviolet telescope that might go up. I'll stop there, and I will see if there are questions that I will stop sharing. And if there are questions, please look at uh, the uh, the chat box and let me know.
Sure, sir. Thank you so much for having briefed us on this topic and navigating us through the basics of electromagnetic spectrum, then how each wavelength range has the potential to explore the space, the limit of atmospheric windows, and the need of observation from space observatories. Then you took us to different ground and space based observatories, including those from India, Astrosat, Aditya, Exposat, etc. Absolutely building on their need aspect with several spectacular illustrations. And you also touched upon the future ISRO astronomy missions. Thank you so much, sir. This was a very wonderful session. Now we have some questions. As you said, we'll take some of them from the chat box. So, Jeet Patel is asking in which spectrum will identify the black hole? Black hole absorbed all the light. Yeah, and how can we identify it? Sir, are you there? Sir, can you hear me?
Yeah, I can hear you, but I'm sorry, you have your next lecture coming up. So,
No issue, sir. We can wait for a couple of minutes and we can take
okay,
a
if you
few
had
questions.
questions, I'm very happy. I'm very happy to answer the questions. Yes.
Yes, so a student is asking in which spectrum will identify the black holes. On black holes, your view on which spectrum should be used.
Yes. So, very interesting question because, black holes are things that you can't see. That is the definition of a black hole. So, you can't see black holes anywhere in the spectrum. But what you can do is that surrounding a black hole, very close to the black hole, the gas that falls into the black hole um, uh, gets very hot before it enters a black hole. It can form a disk around a black hole and swirl around, and the gas that exists around the black hole can become very, very hot because of the gravitational pull of the black hole. And you can show that it can reach 10 to the power 7 degrees. And I showed you that if the gas that surrounds a black hole will emit in the X-rays. And this is why the Chandra X-ray telescope was called Chandra, because it was named after Chandrasekhar, who first showed that how black holes can be formed as a result of stellar evolution. It was named after Chandrasekhar, and it was sent up to find black holes, not by directly observing them, but by observing the gas that's falling into the black hole. And the picture of Centaurus A that I showed you was actually the picture of the gas falling into the black holes. We have detected a lot
All
of
right.
them now. Yeah.
Okay. So another question is how can Aditya L1 payload data be used to predict CME events in advance?
Yeah, absolutely. So that is one of the reasons why Aditya L1 was launched. You can see that it is very far away from the Earth, so that it can observe the sun without the Earth blocking part of the view, right? And so 24 hours it can observe the sun from a very high distance. And so what it is doing, it is taking ultraviolet pictures of the face of the sun, the surface of the sun, which is through the SOOT instrument. And then it is also taking spectra of the corona of the sun. Uh, so when a CME happens, a coronal mass ejection, what happens is that amount of charged particles is emitted from the sun. You can actually see it in the SOOT images. It's happening one face of the sun when things are coming out, and you can see the effect in the corona by looking at the changes in the spectrum that is the VALC instrument, which is the other instrument on Aditya L1. So together you can actually figure out that a coronal mass ejection has happened, and of course from that you can get warnings of which ones are coming towards us, towards the Earth.
Yeah, so you talked about stars and galaxies in your session. There's a question whether electromagnetic spectrum be used to study exoplanets.
Yes. Now, there are many ways of studying exoplanets. You can, of course, detect exoplanets in the optical by looking at, and that's how it is done, by looking at eclipses or looking at the dynamics of stars, where you can't see the exoplanet, but you can see the wobble of the star and things like that. However, once you've detected an exoplanet, you can study its atmosphere, and in the atmosphere there will be spectral lines that belong to molecules, and these molecules can be connected to life and things like that. So in that way, what people are doing is they are trying to build instruments that and these spectral lines will be in the infrared, in the near infrared. So you need to go to space and observe these spectral lines in around the exoplanets, in the spectrum that comes from exoplanets. This is what JWST is already doing. JWST has observed many exoplanets from which spectral signatures have been found, which could be from their atmosphere. And this is one of the reasons why ISRO is planning to build a similar instrument, much more sensitive, much more high resolution, that will go into space, that might look at exoplanet atmospheres.
All right, sir. Sir, one another question is can we determine the age of a celestial body observing the light emitted by it?
Um, Not directly. There are many ways of connecting it to physical models that can give space. For example, if you see the light emitted from something at different wavelengths, then you figure out the spectral distribution of the object, or you can observe a spectrum. Now, the spectrum of an object can be modeled by its physics. For example, the spectrum of a star can be related to the spectral the models we have of stars. And as stars evolve in age, as they age, their spectrum changes. As I said, very hot stars, which are young stars, are ultraviolet dominated, and then they go towards being infrared dominated. So the model itself will tell you the age. Just by observing, the observation doesn't tell you. Yeah.
One last closing question from my side.
Yeah.
So, in the beginning of this session, you showed a very beautiful as well as very informative picture of sun in
Yeah.
different spectrum range.
Yeah.
So, sir, any spectrum of the electromagnetic radiation which has the most potential to be explored, one comment on that, and another, given the potential of electromagnetic spectrum, do we think there are other ways like gravitational waves or neutrinos or particle astronomy, as you also touched upon a little bit? Maybe you can just show some
Yeah,
light
so
on
there are
that.
many, I mean, there are many parts of the spectrum that has not been very adequately explored. The very high energy end, like the gamma rays or hard X-rays, are also provide amazing information. India does not have a near-infrared telescope. Near-infrared gives you quite a lot of information with exoplanets, but also with high redshift objects, as you can see what JWST is doing. And also in the microwave and radio region, there is quite a lot of space to study the cosmic microwave background, for example, which gives you information about the early universe. Certainly, gravitational waves is a new subject that is coming up, and one needs to follow up gravitational waves. I will talk about it in my next lecture, which is about multi-messenger astronomy, where we look at how gravitational waves are connected to electromagnetic waves. I will do that. Thank you.
Thank you, sir.
Thank
It
you
was
very
a
much.
very illustrious session. And thank you
Thank
so much for sparing out your valuable time for our audience. Thank you so much.
thank you, and thank you for being so patient with me. I had a horrible internet connection. Thank you.
Thank you.
A very good afternoon to all of you. In today's session of ISRO START program, Dr. R.P. Singh, Director, Indian Institute of Remote Sensing, ISRO Dehradun, will share his thoughts on the topic Principles of Remote Sensing. A very warm welcome to you, sir. It's my pleasure to read out sir's biodata for the participants. Dr. R.P. Singh received MSc degree in physics from IIT Delhi and PhD degree He is Associate Fellow of Gujarat Science Academy and Chief Editor, Journal of Geomatics of Indian Society of Geomatics. He is the recipient of prestigious Professor P.R. Pishoreti Memorial Award 2005 of Indian Society of Remote Sensing. Now I request sir to deliver the talk.
Thank you, Dr. Charu, for the introduction, and welcome all the participants to the START 2026 session. And we are now going into the second session on Earth observation. And we know that Earth observation is done through a technique called remote sensing. So in this topic, we are going to discuss the basic concepts involved into remote sensing in reference to the Earth observation. And it will be a more of a overview talk where I'll be telling you the broad fundamentals. And I assume that the subsequent talks later on would be followed on specific topics like the thermal remote sensing, microwave remote sensing, hyperspectral in detail by my fellow colleagues. So one good thing is that you have already gone through a very good talks on orbital mechanics and the electromagnetic spectrum, which forms the fundamental of remote sensing also, because these concepts are involved. So this concept will further support you to understand this topic well. So let's start with the basic definition of remote sensing. It is the science of making inference about material object from measurement made at distance without coming into physical contact with the object under study. So what you do, you detect objects, measure object without actually coming to physical contact. And but actually it means a technology of acquiring information about Earth environment, either placing instrument on the aircraft, balloons, space-borne things, or those platforms. So practically, it is one of the important tool for Earth observation, which is used in deriving various properties and processes on the Earth. This remote sensing, while used in the Earth observation, mostly uses the concept that light is made up of electromagnetic radiation, where electric and magnetic field vector uh, they compose the light radiation, and light also has few property which is helpful in doing remote sensing. One is the wavelength. What is the wavelength of light? Wavelength is the distance between successive wave crests or trough in a harmonic wave. Generally, the light what we see through our eyes, and they varies from 0.4 micron to 0.7 micron. But remote sensing, you use many other wavelengths also. The other term widely used in remote sensing to identify the electromagnetic radiation or the light is the frequency. And what is the frequency? Is the number of wave oscillation per time. And one more important term you will be listening later on is the polarization. Light has a specific property called polarization, which refers to direction property of light with a specific reference to vibration of electric vector and its orientation with respect to reference plane. A light can be unpolarized or polarized. It means its electric vector is either rotating in all sort of directions or restricted to a particular plane. Depending on whether it's restricted, is a polarized light, and if it is randomly distributed in all the possible plane, it can be called unpolarized light. Mostly in optics, when we use the remote sensing, light is unpolarized, the natural light is unpolarized. But when we generate light for specific application, particularly in active remote sensing, they are polarized in particulars. So we'll be discussing this concept later on. And most important thing is that while doing remote sensing, where you place your sensor. It can be very close to the object also, but as I said, in Earth's observation, you have to place it certain place. So generally, the broad two category comes. One is the polar orbit, which is sun synchronous in nature, which is generally kept at 500, 600, 700, 800 kilometer above the Earth. And second is the geostationary orbit, which is sensors or satellites are kept into 36,000 kilometer. Why we do so? Because in polar orbit, you continuously rotate the Earth. In the process, you scan the whole Earth. But and when you scan the Earth, your orbit is chosen in such a way that all the time the same local time is followed. It means illumination of the sun remains similar. But in the geosynchronous orbits, you come to a stage, we come to a height where the satellite and Earth becomes, the rotation becomes similar, and you start seeing only one particular place. You become stationary to that place. And mostly satellites are put into equatorial things. Such kind of orbits are mostly used for the meteorology or the communication also, such kind of things are done. There is another kind of orbit you might have heard from the early talk, is inclined orbit. Sometimes you put things into inclined orbit. Generally, these are put at lower altitude to take more revisits, take more pictures of Earth, more than the polar orbits can do. But then your area coverages become limited to certain longitudes. And here, the illumination is not constant. They will pass from different local times, so illumination change. But many a time, like many radars, many things, they do not require any sun synchronous orbit. So you take help of them. Like TRMM was a very important mission for meteorology. It has radars and it was evolving in inclined plane. So looking at the uses, people put into the polar, the inclined, as well as geostationary orbit. When you take images from polar, since they are at lower altitude, as I said, you get more details of it. India has plenty of polar orbiting satellites with a lot of good cameras. You can see in images that you are seeing a very high resolution image on the right side that is called Cartosat. It can take pictures of 1 meter, 2 meter, even better than that. LIS-4 camera, 5.8 meter resolution, LIS-3 camera, 23.5 meter resolution, even a wide field sensor. You can see a larger swath. So these satellites are designed such a way that it can take different swath depending on the application and take different spatial resolution. I will talk about those kind of concepts of resolution later on. Let us see an image from geostationary orbit. If you simply go above the polar orbit, and so you go to 36,000 kilometers, you start seeing a disk of the image. This is one picture from where our INSAT 3A CCD camera is looking over India. And here, whatever you are seeing red is basically green. It is because this image is called false color composite. And in this false color composite, the red color is given to a wavelength called near infrared region, which reflects where vegetation reflects very high. So the terrestrial scientist has a culture of giving them as a color, red color, because NIR anyway doesn't have any natural color. So whatever green looks red to you. So you will be seeing many times, I will be showing you images, they are basically false color composite. So convert something like that. When you see red, think it is a green area. The third orbit nowadays quite popular, and in the previous talk also you were listening, is Lagrangian point. Lagrangian point is where is around 15 lakh kilometer away from Earth, and there the gravitational fields of the what you call the Sun and Earth balances out in a sense that the orbit becomes stationary there, and you see a illuminated what you what you call all the time illumination. Generally, this kind of Lagrangian point L1, many missions are there, including Aditya mission. You heard the same the ISRO made for studying the CMEs and the solar flares, looking at sun. But there was a mission called Discover, which also aimed to see the Earth from that point of view. So right picture shows you how Earth look from 15 lakh kilometer. It is from L1 point. It is one of the unique mission, I would say, that because there are not many satellite looking Earth from that mission, because we are too far away from that. But still some advantages are there for looking that. So it is also one of the place from where you can look the Earth also, although it is meant for the sun and other astronomical objects. In the right figure, you can see the blue Earth as well as some kind of dark body called Moon. So since Moon is only 4 lakhs kilometer away approximately from Earth, so from 15 lakh kilometer, you can see both Earth and Moon. So this orbit is also can be useful in remote sensing. So let's go to the kind of sensing system we employ. So formally, they are called active and passive. Active one, which has their own source of radiation, and you call LIDAR, you call synthetic aperture radar, you call spectrometer, you call altimeter. These are the terminology used for this kind of systems. But at the same time, they're passive sensors. Passive sensors means they do not have any own source of light. Whatever the emitted signal come from the Earth or the environment, they record them. And we call them radiometers, we call them spectrometers. They can be in optical region or microwave region. Here you can see the spectrum, electromagnetic spectrum, and mostly you will see that remote sensing is done in a part of the UV region, mostly visible region, and then short wave infrared and thermo infrared, and also in some of the microwave region, we call them P band, L band, S band, C band, X band, Q band, K band, K band. All these bands have certain advantages and some specific uses. That is why these missions are made. So idea of showing you this curve is remote sensing. The active and passive sensors are used, and they are operated in a specific wavelength region, and that is because of their applications. Okay, let us see that what are those regions. So in remote sensing, generally gamma ray, X-rays are not used much. Astronomy, of course, they are used. So as I said, UV, visible, infrared regions, and microwave. And the most popular is, of course, the visible region, because also man also see through our eyes from this region. So as I said, visible belong to 0.4 to 0.7 micrometer. Beyond that, what we can't see, it is called near infrared, 0.7 to 1.5. Many instruments are put here. Vegetation has a huge reflectance in this region. Short wave infrared, 1.5 to 3.0 micrometer. This is very important to detect the snow, because snow, although has a high reflection in visible and near infrared, suddenly there's a drop in the short wave infrared. This kind of techniques people use. Then comes the long wave infrared, 8 to 15 micrometer. This is a place where we estimate this. This is the region by which we estimate the this land surface temperature and do various meteorological applications. And then there are far infrared regions also. So let me, before we come to the actual our discussion on remote sensing, we have to understand the concept of a instrumentation or sensor. What does a sensor do? It has a sensor is an object which has certain optics, four optics, and four optics is designed in such way that it can see a particular region. The bigger region is called swath, and what is the smallest region is can see through his field of view. This is called instantaneous field of view. We also call it ground resolution element. This is the minimum area it can see from there. Okay, so once it detects a signal from a instantaneous field of view through a angular aperture, which is dictated by the four optics, it is collected through a optical system. The light is gathered. Later on, light is dispersed into different colors, either using certain filter or some prism or grating or whatever it is, so that you make out the so-called white light coming into different red, green, blue components, and then you detect those energy of light through a detector. Detector can be of silicon or many other kind of systems are there. Infrared, they are different detectors. So looking at the region in which we are working, you detect the signal. After detecting, you convert into digital to analog to digital conversion you carry out, and later on you record those things and do send them through a telemetry to ground receiving station. So there is a big antenna or station on the ground. They receive those signals. Later on, those signals are recalculated into energy units, and then scientists are able to analyze those energy units from coming from certain terrain or the atmosphere, and they are able to carry out the application. So this is the broad chain in which this remote sensing works. Technically speaking, as I said, there are optical and microwave region, and in that also there is a passive and active system. So what you call, there are few sensors called cameras. Generally, the way conventional camera you use in 0.4 to 0.7, there are certain sensors called multispectral sensors where you choose certain wavelength. You don't work continuously in all red, green, blue, but you have a choice of choosing certain wavelength. You call multi-center sensors. Then there are some infrared radiometers. We can observe even temperature. They can be bolometer, they can be MCT. They are the detector types. They are something called sounders also. There is a technique by which not only detect the temperature of the surface, you can also know the vertical distribution of the surfaces. I mean, the distribution of temperature and humidity. We call them sounders. Generally, they are hyperspectral spectrometers working into thermal infrared region. Hyperspectral instrumentation also work in the optical infrared region, and they are used for detecting the minerals and even trace gases, and many other things are done. So there are a class of instrument called spectrometers. Uh, in active sense, there are lidar, there are altimeter made which decide by the lasers. Microwave, you have microwave radiometers, microwave sounders, synthetic aperture radar, scatterometer, altimeters. So these are the terminology. People use them to observe various processes, and they work in different wavelength region. I have shown you in this table, and each one has certain scientific principle by which they devise their properties. Today we'll only see the overview of it. I hope in the subsequent talks you will be given details on each of it. So let's again go. What is active remote sensing? As I said, remote sensing methods that provide their own source of radiation to illuminate the terrain. So radar and scatterometer lidar is such example. You can see India here. This India's picture is taken by a synthetic aperture radar made by ISRO. We call RESAT 1. And you can see the whole India. The colors are slightly different. It is conventionally not similar to what we see in other optical regions. And do you know the advantage of this imaging? Advantage of imaging is that you can take pictures in night also, because they have own source of limitation. So, and these pictures can come even through clouds, because they work in C-band. C-band has a ability to penetrate the cloud. So even if there are clouds and raining things happening in particular monsoon season, terrestrial pictures can be taken. So it becomes very useful to detect the flood and many things using this kind of radar. Passive remote sensing, as I said, it is the remote sensing of energy naturally reflected or radiated from the terrain. Here you don't put any source of light. Sun is a source here. When we use sun, we call it as a natural source, and whatever reflections come in optical region, this is called passive remote sensing. Many times, even night also we can do, even there is no sun, because Earth itself emits radiation. Earth is a certain temperature, 300 Kelvin or so, and any body which has certain temperature will emit radiation through because of the Planck principle. That radiation is detected by the radiometers. Instruments are called radiometers, and then you are able to know the temperature and many more property of the surface and the atmosphere. Let us see one example. I am showing you an example where you are seeing the India in 19 gigahertz and 85 gigahertz. What you are seeing here, you are getting more or less what you call energy because of the temperature and emissivity. So you convert that energy into a measurement called brightness temperature. So it is the image of a brightness temperature observed at 19 gigahertz and 85 gigahertz. Mostly we'll see that the energy coming low, that is black areas, are because of the low temperature. Okay, in the right hand side you can see, but in left hand side see many areas are even black. Particularly you see the Bihar and even the Gujarat coast are part of Bengal, but they're not because black because of the low temperature. They are black because is this particular time there was a flooding situation, and when there is water on the surface, water has a very low emissivity in the microwave region. So it reduces your brightness temperature. Brightness temperature is nothing but the product of emissivity and physical temperature. So such information, such kind of imaging in a passive mode of microwaves has a lot of application to estimate the terrestrial property, as well as in fact they are used to they estimate the rainfall over the ocean. When a ocean without rainfall and ocean with rainfall has a variation in brightness temperature, and the meteorologists know these variations is caused by the extra emission due to the raining clouds, and that helps them to compute the rain rate. So such field of remote sensing also has many terrestrial and meteorological and oceanographic applications. Let's talk about a very fundamental concept in remote sensing. It's called signature. Signature of any object or its condition comprise a set of observable characteristics which directly or indirectly lead to identification of an object. So every object has certain signature, specific patterns of its measurement of variable. Generally, this characteristic can be terms of spectral characteristic, spatial characteristic, temporal characteristic, and polarization characteristic. And the signatures are always not very deterministic. It's not that they are very unique. They are some statistical in nature. They have some small variation here, there, because nature has a lot of intrinsic variability. But yeah, broadly, most of the targets had certain signature. And the basic purpose of remote sensing is to find those signature, and based upon signature, try to see the unknown areas and trying to decipher the property or identify the target because of the its signature being observed from satellite. Okay. So fundamentally, in spectral signature is set of characteristic by which material or an object can be identified. Now, what is this characteristic? It is a reflectance versus wavelength. When you find a distribution of reflectance with respect to wavelength, you'll find different curves coming out. These curves are called spectral signatures. And what they tell that like on the top of it, you are seeing some black and dotted line. They are of clouds and snow. They say that in the majority of the lower wavelength region of 0.4, 0.6, 0.8, what we call visible region, they are very high reflecting properties, 80 to 90, even 95%. We know them, they are clouds because they reflect high. But water, see the blue one on the bottom, it reflects very low in those regions. So our objects, they reflect differently in different wavelength regions. Like cloud reflects very high, The water reflects very low, and vegetation and the soils reflect medium wise. But their characteristics changes from wavelength to wavelength region. Like snow, if you talk about the dotted line, suddenly drops in the region in 1.4 wavelength region, the Swift region, whereas cloud doesn't drop so. It has a property of that. Although both has a water content, but one has a solid form, other is the vapor form, and their characteristic, the spectroscopy is different, and that property is used by scientists to discriminate them. Similarly, you see a green curve, very famous one. You see green curve is having a low wavelength in blue, suddenly low reflectance in blue, relatively high in green, again low in red, and then huge reflection come in the near infrared region. Since we are not able to see infrared region, we see vegetation green because green wavelength 0.5 around, you see more reflection compared to 0.4 blue and 0.7 red. But no, even beyond our eyes, you'll find that vegetation looks much brighter. If you have given a capacity to see beyond the red, you would have seen vegetation very bright in some other sense. Anyway, cameras are able to do so. So this particular characteristic, like near infrared region, you see such a high reflection, and you do not see them into blue or green because they have a pigment called chlorophyll. They absorb in blue, they absorb in red region, but they do not absorb in green and near infrared. And near infrared, there is peculiar property called total internal reflection takes place within the leaf, which is because of the air and the water being together, and light somehow goes through a critical reflection, and that is why this phenomena takes place. This is very unique phenomena. It makes it different from the cloud, it makes it different from the soil, it makes it different from the water. And that's why the remote sensing people are able to know about the vegetation, the type of vegetation, even their properties. Same way, the water also has although low reflectance, but it is varying with respect to its condition. It is a clear water or the turbid water. So scientists have trained their model to decipher through their spectrosignature. So I want to emphasize one important variable called vegetation index. It is also known as NDVI, Normalized Difference Vegetation Index. It is very popular, so I thought to share with you. Since near infrared reflects very high and the red reflections are low, so what happens in a green, in a what you call a good vigor crop or a green leaf? So the difference between the near infrared and red, when computed in a fashion that rho n minus rho r upon rho n plus rho r, where rho is the reflectance, you will find this difference, the contrast, which is normalized, becomes very high. Like 50% is near infrared, 8% in what you call red is a good contrast. But what happens when the leaf become brown, senesces? This 50% become 40%, but this 8%, which was coming from red light because of absorption, suddenly becomes 30%. There's no absorption from chlorophyll. Now the contrast has reduced. It is between 40 and 30. So the NDVI value becomes less. This is the principle that one computes the NDVI, that is the difference between the near infrared and red, and divide by its summation and compute a number. This number starts telling about the greenness and the vigor. And what happens? If simple principle when employed in the satellite, so you put a satellite with sensor, put a filter in near infrared, put a filter in red band, what you see? Some of the regions start looking brighter in the infrared region, those who are having vegetation, and those region becomes darker in red because there is absorption. By simple principle, if you compute the NDVIs I was talking about, you can know all the green areas. Not only you can know green area, you can find the types and their vigor and the productivity. And it is a very popular index. And every day or every month you can find the condition of greenness over the world. So it is very popular in remote sensing. Let's talk about the spatial variations. Obviously, the shape, size, and textures object they lead to the differences in the reflectance, and the scientists are tuned to find the differences, and that's how they interpret the objects. Temporal variations are equally important. Many times, suppose I'm not able to distinguish an object in a given instant of time because its spectral signatures are matching or its spatial variations are similar. So what you do, you track them in time. I'm showing a curve here. I'm tracking a rice region of Punjab, its greenness in time. What I'm seeing, in one time of frame, because of cropping practices, it is following some phenological characteristic. When the farmers has changed their practices, their characteristic got changed. They started showing early rise compared to other one. This is possible to see through a temporal variation. And nowadays, because of the advent of high resolution imageries from satellite of the order of 1 or 2 meter, and daily or near daily coverages from planet and many other satellites, you can monitor the transplanting processes, the harvesting processes, and you can see them. In the starting picture, there is no crop. Suddenly, transplanting took place, and the field becomes black because water is absorbing one. And then you start seeing redness. As I said, redness is greenness because we are giving a false color composite knowledge to you, and then most of the time it is grown here. End of day in September 11, the crop is harvested and you start seeing the farm again. Such kind of temporal knowledge has become now possible to see a farm through remote sensing. I was talking about the polarization variations also. Polarization is a said property of light when this electric field is confined to a particular plane. So radars are made to use this property. So what they do, they have different polarization. Sometimes they transmit light in H horizontal polarization and they receive in vertical polarization. Sometimes they transmit in H and they receive in H also. Depending on the configuration, what kind of polarization they are using, they get different pictures. Particularly, this is a picture of an NVSat satellite in HV and HS polarization of C-band. You see HV signatures or the backscattering are lower as compared to the HS signature. Obviously, if you send into H the horizontal polarization, your component in vertical would be lesser when you see them in a backscattering mode. So such properties are used by the scientists to know the different terrain characteristic because different terrain induces different polarization or depolarization characteristic of interactions. Let's slightly come to the part of going beyond the optical region. We call it as infrared imaging. What is infrared imaging? Imaging is way when we are not able to see. It's beyond 0.7 micrometer, beyond visible. And how it is come? That Planck says that any body at certain temperature will emit certain radiation. And in the Planck law, you know, this energy received is a function of some constant, the wavelength, and the temperature. Okay, so given temperature and given wavelength, there will be characteristic energy, and by this, if I place my radiometer or call sensor in certain wavelength region, 10 micron to 12 micron or something like that, I know at what temperature I would get what energy. So depending upon I get certain energy, by Planck law, I can estimate temperature. And in the ground, in the below picture, you can see that we can easily compute temperature of the Earth or any planetary body for that matter using this law. What this says? It says detect the energy. You know Planck law. How does a black body behave? Black body has a characteristic energy at given wavelength and given temperature. So if I have got this much energy, if I'm working in this wavelength, I will be able to know the temperature. Of course, it works for black body, and black body is an ideal substance that absorbs all the radiant energy incident on it and emit a radiant energy at maximum possible rate per unit area at each wavelength for any given temperature. Actually, no actual substance is true black body. So we have to take the the concept of emissivities, that black body has emissivity 1, but gray bodies do not have it. So that emissivity start playing a role. So scientists take care of it, either estimating emissivity or using emissivity to know the correct, estimate the correct temperature. This is one example which shows that I see some rocks in visible region, the RGB, red, green, blue. And if I same thing in the long wave region, they look much different. And if I take a spectrum of emissivity with respect to wavelength, these minerals and those kind of materials like feldspar or quartz I am showing here, they look very different. And that is why these principles are mainly used, the infrared principles are used to detect the mineral in Earth as well as many of the planetary bodies, particularly the Moon and the Mars. It has been very popular because this particular region has characteristic signatures of many of the mineral in this 8 to 12 micrometer region. Now let's come to one important property which is often talked and we need to know them, is the resolving power. So what is resolving power? How do you characterize the instrument? It's characterized by certain resolving power. So it's measure ability of remote sensing system to segregate closely spaced targets. Are you able to see them distinctly, even the close targets, and how you are able to see them? So there is a Rayleigh criteria. Two objects can be just resolved if the peak of the airy pattern of one falls on the first minimum of other. So those who have studied physics in the college, you are studying the physics, you might have heard this law that when I see two objects, the peak of the first the airy pattern of one has to fall on the first minimum of other one. The angular separation of which this happens, and we say it is resolved. In practical sense, it is sensor ability to record closely spaced objects so that they are distinguishable. So we practically call IFOVs. What is the meter resolution at which I can detect the smallest object, the instantaneous field of view? ISRO has made many cameras. I'm showing you some pictures. The first one is the list 3 at 23.5 meter, list 2 36 meter, list 1 72 meter, and the fifth was 180 meter or so. So you'll see them when you look at different meters. The resolving ability varies. So it is ultimately the instantaneous field of view of a remote sensing system, which is defined as a geometric image of detector aperture on the ground. So what is that image? Whatever the dot in the sensor you have, no? Geometric image, if you see on the ground, it will the kind of shape or kind of area it will cover is known as IFOV. Alternatively, it may be thought as a size of ground pass that will be imaged onto the aperture of a single detector. It is basically projection of single detector on the ground. That much field you are able to see them. But even if your IFOV or resolutions are same, but your cameras can look at different images because it is also the kind of optics, the kind of lenses you have used. So there is a concept called modulation transfer function. So while this light goes through your optics, it gets modulated. Your contrast in object plane and your contrast in image plane changes. And the ratio of this is called modulation transfer function. And this is also a function of spatial frequency. If things are varying fast, then the transfer function is different. And if things are not varying too much, the transfer function will be very high in the low varying target. So it is another way of defining the spatial resolution. Then comes the spectral resolution. If I have certain spatial resolution, I can see at different wavelength region. When I say at different wavelength region, what does it mean? I have to see within certain bandwidth. There is nothing like fixed wavelength. So every filter we use to distinguish or detect the light passes through a filtering mechanism. The spectral bandwidth is the in which data is collected, the width in which is collected. Many times we call full width at half maxima. So whatever you observe, generally it has a Gaussian pattern. I'm showing you for some representative example of green band and red band. So you see there is a cutoff frequency. Here you are seeing 520 and 600 nanometer. Beyond that, we are not able to. We don't want to detect light. So within them, what we detect is the bandwidth. And ideally, we have to see that it is the width at the half maximum of that related spectral response. So this is defined for every sensor. So sometimes we say our spectral width is 10 nanometer, sometimes we say it is 50 nanometer, or some certain number. So one has to characterize. An idea of putting the filter is that every wavelength, your detection, your abilities are different. Like I'm showing you image on the down. If you see same region, agriculture region, in green and red, NIR, and then fast color composite. I was talking all red in fast color is actually a very high reflecting in the infrared region. You are seeing white color, no? Third picture from the left. But in the red, second picture from the left, it is dark. The same principle. A vegetation would absorb the red band relatively, it will absorb more, and near infrared you see very high and bright signal, and that is how it seen in the false color composite as a red, because we give red color to infrared region, we give green color to red band and blue color to green band. So this kind of false color composite is created. Radiometric resolution is one of kind of thing. The number of bits in which your sensor is encoding your signal. Whenever I get a certain signal, it becomes an analog signal to me. I have to have an analog to digital conversion. I have to convert it into digital numbers. I can convert in 2-bit, I convert in 4-bit, 6-bit, 12-bit. More the bit I convert, I'll get more details of it. So capability of sensor to differentiate the smallest change in the spectral reflectance emittance between various targets generally is represented as noise equivalent change in reflectance or temperature and represented by bits. So obviously, if my bit is lower, my number of information, the type of information is low. As and when my bits become more, I see more detail, but it's not always true. At a certain point of time, certain bit things get saturated. Temporal resolution is important, I said. Its capability to view the same target under similar condition at regular intervals. I'm showing you two pictures. One is the insert picture on top, and in the bottom side, I'm showing you a Punjab region in India through our IIRS satellite, which is polar in nature. The top picture is inset, so your revisit is very fast. Half an hour you can see the region, because you are placed in a geostationary orbit, you have ability to take faster picture. So temporal resolution is very high. But when we start seeing in detail, many times my resolutions is not that fast. I see detail in spatial domain, but temporally I start seeing after 12 days or 16 days, Landsat 16 days, we used to see in 24 days. So depending on our own satellite and the geometry, this changes. Like our advanced base camera, when we made with certain swath, it sees in every 5 days. Generally, agriculture scientists thinks 1 week is good enough for them to see them. So they are designed in that sense. But for meteorology, 1 week is too less. It has to be seen in hourly, half hourly, even many times more than that. So it is time interval between the imaging collection over the same geographical location. Looking at the application, you design your camera or system and their orbit in such a manner that it meets your temporal resolution. As I said, the temporal resolution is important also because if I see a form, I am seeing you on top left, it is a form of Pantnagar, and all red colors again I said is the crops, green crops. At one given instant of time, I took picture on 31 January 2023 and created a single day FCC. You are seeing variations, but if I put more number of observation in the second right picture, lower right, I put 3 dates on that. Suddenly, my distinction is improved. So the multi-temporal observations are important many times when the single dates are not able to distinguish things adequately. Anyway, we'll go to bit of it interaction processes happening on the ground. So in remote sensing technology, we have seen how sensor works, how platform works, what are the definitions of resolutions. Now, some more characteristics we have to know because they will help you to understand or see and listen other talks which will be coming because they will be using this terminology very frequently. One term is called emissivity. What is emissivity? A ratio of observed flux from a body. Suppose there is a body, it's a gray body, I am observing its energy. Of course, at given temperature, it will give me energy. It's the ratio of observed flux, what I estimate energy from the body, to that of a black body and the same temperature. Think if it is a black body, if of the same temperature, what energy it would have given? The ratio of two is called emissivity. So if it's totally black body, I am doing this, it will come 1. But if it is gray body, generally energy what we will get is lesser than what it would have given a same temperature by black body. So this emissivity varies from 0 to 1. There is something called absorptivity. The fraction part of incident radiation that is absorbed by the surface. When light comes, it will be absorbed. So what is the fraction it got absorbed? The reflectivity. The fraction part of incident radiation that is reflected by. What is the fraction? So if my 100 unit of light came, and I got only 50 units, so it is 50%. If I got only 10 unit of the incident light, I will call it is 10% reflectivity. What is transmittivity? Many times, now it will not only reflect or absorb, it gets transmitted from the material. If it is transparent, the fractional part of radiation transmitted through the medium. So end of day, whatever incident light comes, whatever is reflected, it can be absorbed, it can be transmitted. End of day, the reflected plus absorbed plus transmitted would be conserved. It will be the same energy which has fallen. So energy is conserved in that sense. When you see objects, we have to know some are specular reflectors, like mirror. If you see, if you send a laser or light, it will go to certain angle to some other place because it is smooth surface. But natural surfaces are not reflectors. They are diffuse. We call them Lambertian. They generally reflect in most of the directions, all directions. But then, all are not that idealized. Some, they have preference of sending light in certain direction, but they do send in other directions also. So they are less idealized surface reflection. So nearly diffuse, we call them. They are nearly specular, but it is a specular which is totally follows Snell's law. Whatever angle I send, the reflection angle also becomes similar, and others are Lambertian, means started sending light. So generally Earth surfaces are Lambertian in nature, or say less idealized reflection, and the characteristic, whether it is a Lambertian or specular, is known by a term called bidirectional reflectance distribution function. I am showing an image where if you take a picture from, this is basically cartosat image of ISRO, where you take a picture from Nadir just beneath you and you see at 26 degree, some inclined, your reflectances get changed. It is because body, the surface, the target has a bidirectional reflectance. The reflectance vary with respect to the illumination and viewing geometry. To perfectly carry out the surface characteristic, particularly in case of planetary surfaces, where the sun direction and view direction constantly change, scientist has to master this BRDF to know the property. Let me talk about some terms used by remote sensing scientists. One is the radiant energy, how much joule of light you are making incident or reflection. Second is radiant flux. What is watt of that particular light energy coming to you? It is nothing but radiant energy emitted or incident upon a surface per unit time. So one is joule, other is watt, we call radiant flux, and most important, what we observe mostly from our satellite is radiance. Radiant flux per unit projected area per unit solid angle. So we call watts per meter square per steradian. So it's also a function at what solid angle you are looking at it. So these terminologies are used when you detect the energies. And now I'll talk a bit of atmosphere and related issues. When you are a terrestrial scientist, you also know the Earth is enveloped by the atmosphere, having troposphere with varying density, and they have gases and many of the aerosol particles into them. So what happens? Light is not only modulated when you see from satellite by the this surface is also modulated by the atmosphere through a process called gaseous absorption or scattering by molecules or aerosols that we need to know them. Know them for the two purposes. Either we want to know their property of atmosphere itself, or we want to correct the influences of atmosphere. Okay, so this atmosphere has specific absorption in different wavelength region of S2, CO2. So generally for terrestrial purposes, we use the spectral domain when it is transparent. Atmosphere is not creating a hindrance. But for many of the atmospheric applications, what we do, we choose the wavelength where atmosphere is actually absorbing to know the atmospheric property. And this all happens because of scattering in the atmosphere, particulate matter, depending on the size. If they're very small, they do Rayleigh scattering, the molecules do. If they are aerosols or medium size, they do Mie scattering. And if they are water vapor in the clouds, they do non-selective scattering. And that is how you see different colors. You see blue sky, white cloud, and many more things like that. So, end of day, when we know those concepts and know the radiative transfer and their characteristic, we are able to solve the atmosphere. For terrestrial application, we call atmospheric correction. We are able to remove the influences by atmosphere. But for atmospheric scientists, we are able to know the property in terms of aerosol optical thickness and trace gas concentration. Images are important in remote sensing, so you can see they are pictorial representation of scene recorded by remote sensing, and now you can see any ecosystem, call it fields or the snow or the desert or the pictures taken from IIRS satellites of different ecosystem in India, and every image has a certain digital number. As I said, energy is initially converted into a digital number. It is a value assigned to a pixel. For a red band, it will vary by some number. You can see on top, you can see in this image, central part is a big forest system we call Satpura forest. The picture is taken in the central India near Bhopal. So all blackish region on top right image is the red band where absorption taking place, but same thing is looking brighter in near infrared band because of this forest is giving huge reflection there. So what you do, based on the dn value, calculate into energy units, radians, and later on this energy is further calculated into reflectance, a ratio of radiant flux reflected by the body to the incident flux. And this is the reflectance later on used for calculating NDVI or put into various model to know the productivities and various other properties. Most important thing is the big branch of remote sensing science is to do classification and pattern recognition. It is of two types, supervised and unsupervised. Supervised is there when I already define certain known targets, calculate the signatures, and know, okay, my target of interest at this signature. Later on, I allow computer to every pixel to be classified into the patterns which I have told them. Okay, this wheat or this is gram or this is forest. You convert into patterns. So it is I who have supervised to such signature. Many times I allow computer to automatically make groups of the pixel based upon intrinsic spectral signature, and later on I define a name to the particular cluster. It's called unsupervised classification. But end of day, you have an image, and the image is further calculated into forest, crop, wasteland, fallow, water, and sand. We call pattern recognition. We call this as a land use, land cover mapping. There are few techniques which will be talked in later on. We dedicated lectures are there. That is called hyperspectral imaging spectrometer. There we are not only in few bands, we see the reflection in continuous wavelengths. So technology of detection is also different, but pattern recognition and processing are different. These techniques are known to be much better and more accurate than multispectral, but they are complex in the processing. This one small good picture you can see here, that one hyperspectral image from NASA has seen a region, and by that you now not only know the type of the vegetation, you can know even the pigments, chlorophyll, anthocyanins, carolinite, because every leaf has some different pigmentation. So hyperspectral and the imaging allow us to know the pigmentations also and mineral characteristics. Another very important application is SAR interferometry, in which you not only see the images, you are able to even see the deformations through a concept called interferometry, where the pictures are taken either by through antenna or at two times, and the phases are exploited to make interferogram, and the interferogram carries the the the, the height variation or any changes, subtle changes in topography. NISAR satellite is a good example. It is giving SR interferometric observations. Another good technology is LIDAR remote sensing, where you not only see the vegetation, you also start seeing the vertical distribution and the structures of vegetation. And it is very helpful in knowing the biomasses, other thing. You can see there are already space-borne LIDARs, JEDI and ISAT, and the world's biomass has been computed because it has the ability to penetrate within the vegetation and bring out the structure property. I would like to discuss with you another concept, slightly different the conventional remote sensing, where detection is not done by the electromagnetic radiation, but it is being done through measuring gravity. So what is done? The mission is called Gravity Recovery and Climate Experiment GRACE. Here we have two satellites, and when they pass over the region, their velocity change or their orbit dynamics change because of the underlying gravity. And because of that, their orbital characteristics, scientists are able to know what is the gravity beneath. And if I know the gravity beneath, I can know many things, the lithologies, the structural properties, even the water equivalent thickness, how much water is lying in beneath the ground. There is a special kind of remote sensing where gravity is exploited, the knowledge of gravity, not electromagnetic interaction bringing you the knowledge. So end of day, I would like to conclude something like that while doing this whole science, there are various dimensions of it. One has to develop an instrument and put on a satellite, launch it, do the data reception, then a lot of computer knowledge goes into it in form of data product, then application, end of the validation. So all technologies have their own uniqueness. That is why different institutions are there to do that. But in the whole end, we are able to find out the uses of it. We call Earth observations. And Earth observation we carry out, we are able to know the application, carry a lot of application in agriculture, the forest, the disaster, the water, weather, urban planning, and climate change in many fields. This itself is a vast subject. I would like to say in summary that all this remote sensing is ultimately for the application in various fields. And not only these cameras has given huge information on Earth, there are similar technologies when we employ on the planetary bodies. Also, we can know many of the properties. I'm just showing you an example. In 2008, when Chandrayaan-1 was launched, we were able to see the water on the polar surfaces. It was the first kind of discovery, and the principles were very similar, like remote sensing. So remote sensing principles are employed not only for the Earth, it can be employed for any planetary bodies. Similarly, we know our Mars mission also had a camera. It also did a lot of remote sensing, and from there we are able to see many processes there, including the flowing rivers and atmospheric processes there. So what I mean to say that the fundamental remote sensing not is only limited to Earth, it is being also tried to be used for very planetary explorations. So here I close my talk. Thank you very much.
Thank you. Principles of remote sensing. You have made the participants aware of the passive sensings and the active sensings, including the spatial, spectral, and temporal resolutions. And you also gave the glimpses of the applications of the remote sensing data sets, which was not only limited to the Earth, but you also showed the applications beyond Earth system. Like you showed some slides on the Mars and applications on the Moon. So again, thank you so much, sir, for this talk. Now I request the participants to drop some questions in the chat box so that we can take up some questions. Sir, we have question from Ms. Sweta, and the question is, why can active sensors operate at night while passive sensors generally cannot?
Okay. This Shweta, these active sensors, since they have their own radiation, so for them there is nothing like day and night. They can impinge any what you call energy on the target, and they can see it. So they night also can see. For passive sensing, of course, those passive sensing, as I said in my talk, passive sensing is because of two things. One is even the sunlight falling, and when we get a reflection, we also call passive sensing. That cannot happen in night because there is no sun. So how the light will fall? So obviously, when there is no light, you will not going to see the reflection. But Sweta, I want to tell you, in passive sensing technique also, even the earth or the target's radiation also can be detected. So it is not that passive sensing cannot be done in night. Passive sensing through its own emission by measuring temperature and their property can be done in night also. That is why you are able to see a lot of forecast in night from the IMD, India Meteorological Department, because our satellite, the thermal cameras are working in night. So passive sensing done by solar reflection will not be there, of course, but the thermal infrared can also be done in night. And active anyway, they have own radiation. Wherever they will put energy, they will get it back.
So another question, Mr. Sandeep Kumar is asking, how is remote sensing used to monitor climate change?
Oh, so Sandeep, this is important question. Uh, Remote sensing actually is one of the important, I would say, technique by which climate change can be done. You know how? By knowing its indicators. Why, how the climate change is happening? How do I know climate is happening? So people say it is happening. A lot of warming is taking place. So glaciers are melting. So, but just monitoring glaciers from last few decades, if I see, and most of them, if they are melting, it's only because something warming up taking place. Otherwise, they will melt? Similarly, we are seeing what is the indication that something happening. This melting is going on. So, this the sea level is increasing. You know, is one of the indicators. So remote sensing has altimeter principles, and they are able to know the sea level. And we have seen that over the time it is increasing. So these are the few measurements which are indicators of climate change. Sometimes, why climate change is happening? Do you know? It's happening because more this greenhouse gas is going into atmosphere. They are the agents. They are responsible for them. So we have to monitor them. The remote sensing has ability to even know about the CO2, methane, and all those greenhouse gases because they absorb a certain wavelength. They will more in number, they will absorb more. So by knowing their absorption property, satellites are able to know the concentration. So again, measuring their what you call concentration, we are knowing the climate change. So the list is quite big. So I would say by knowing the indicators, the agents, and the impacts on the ground where vegetation is increasing, their productivity increasing. If all that I have to know, satellites are giving a lot of, the information not only at one place but the globally because the climate change process is not localized; it's a global process.
Next question is from Miss Arpita, and she is asking, what is the importance of IFOV in remote sensing?
IFOB, I was talking, Arpita, is a instantaneous field of view. So I was telling you, suppose n number of cameras are there. In our houses, we have a lot of cameras. No? Some take good pictures, some take less pictures. And same way satellites, some take coarser pictures, some take detailed picture. Even if I same camera, I put in a what you call a polar orbit, and same camera if I take to the geostationary orbit, much above than that, will it take the same picture? No, their resolution will change. The minimum area on the ground which they were seeing instantaneous field of view of a single detector. If all detector you take together, it's called swath, the total coverage. If I talk about one particular single detector, its projection on the ground. Obviously, if you are closer, you have a smaller, what you call IFOV, so more high resolution. You can see in detail. Suppose take a camera on top of it and take to certain other heights. Same camera, its IFOV will change, it become wider. You will not able to see in details. Okay, so it is the intrinsic property of a camera which defines the spatial resolution. There is a resolving ability, and it is also a function of distance at which you are working from the target.
So Ms. Falgunim is asking, what is the difference between spectral variations and temporal variations?
Falguni, is a good question. These two are important concept in remote sensing. Spectral means if I take a measurement of a target, okay, at given instant of time, I'm not worrying about time. What I do, what is my sensor does, I will measure its response, either reflectance or energy or emittance or whatever it is, absorptance, anything I can measure with respect to the wavelength region. Suppose I am measuring how much is a object reflecting me at blue, green, red, near infrared, thermal infrared, and plot with it with wavelength. These variations are called spectral variations. Every target I said has certain unique spectral. That's how the remote sensing works. No? A snow will have sun pattern, vegetation will have some pattern, and water will have some pattern. Okay, but what is temporal variation? Now, whatever spectrum I have got, suppose I fix up a wavelength or I compute some NDVI or some index out of it, and I track in time. This will increase, decrease, something will happen to it. Suppose it is a crop, it will suddenly become green and then in senescence. So their behavior will get reflected in my measurement. So if I plot my measurement, say greenness, with respect to time, this is called temporal variations. Both are used to identify distinguished target depending upon the uses.
So Ms. Shobana's query is, how often does the satellite pass over the same field? I mean, she's asking about the temporal resolution, and is that frequent enough to monitor fast growing crops?
It's a good question. As I already told you, when we design a particular satellite or its orbit or characteristic, a platform and cameras, those things, uh, we see applications. So what happens? That temporal resolution is one of the important factors. How frequent I want to see them. Particularly crop cases, our observations, experiences has shown crop doesn't grow very fast. Okay, and we have seen if I take observation say from 4 to 5 day or 6 day or week, I will able to capture the various phases of crop. So I define my camera in such a sense, its swath and this thing and orbit, so that it comes again and again and again to see the particular same thing in same interval. I will take very important camera, very useful camera, generally is used by everybody, all of us in monitoring crop. It's called Advanced Wide Field Sensor. We have designed it so that it can take observations of 5 day every time the same pixel, same target in 5 days. Because we felt 5 days is good for the crops, and that we decided we will observe it 56-meter resolution. But same time, this one criteria we have found is correct. But for some other places, it can be different also, looking at the type of crop, which crop you are working at it. And so every application we have to define temporal revisit. Suppose I am working for forest application. I don't need to see them at 5 day. Forests grow much slower than crops. So I can define a 10 day, a 15 day. So looking at applications, I would define my camera accordingly, design and place them in the orbit.
So next question is, can remote sensing technique can be used to figure out natural resource abundant regions?
Yeah, it is the main application. You see, it's the main purpose that my country, natural resources, I want to know. Earlier, we used to know by surveys. Surveys used to take a lot of time. Still, it is done by surveys, but they have their own time-taking process. Suddenly, I want to know what happens to my resources, whether my drought has reduced my productivity, whether forest is getting deforested, or something is happening to some region, or my snow has melted this year, or this year's snow was more or less, because I have to worry about the water in my rivers. So, for all the natural resources, I have to monitor them. And ISRO and many of the countries, other countries also, they have made their system to monitor regularly. And most of the natural resources are, say, agriculture, the water, the forest, the environment, the climate, means the trace gases, the aerosols, the oceans are being regularly monitored to take proper decision, so that in case of eventuality or suddenly something happens and we need to know them, or something is happening to them, and take appropriate measure to solve it.
Thank you so much, sir. Now we have reached towards the end of the session. Thank you again for this excellent talk and giving answers to the queries of our participants.
Thank you, Dr.
again, sir.
Charu, and thank you to all the participants for listening to this talk. Thank you very much.